Hey guys, in this video we're going to talk about solving one variable inequalities. So what is an inequality, first of all? So in the past few lectures we've talked about equalities or equations, okay? So we talked about solving equations. Now an equation is a mathematical sentence that contains an equal sign, right? But an inequality is a mathematical sentence that contains a sign other than an equal sign. Okay, so it indicates that the values on each side make a non-equal comparison. So the prefix in an inequality means not, basically, not equality. So these are the inequality symbols right here. So this means greater than. So when the mouth is opening up towards something, it means greater than. So for instance, if you write 2, that 1, what this means is 2 is greater than 1. Right? Because the mouth is facing open towards the greater thing. Okay, so that's greater than. Now this symbol means less than. So we could write this same thing, 2 is greater than 1, but we could flip it around so that the 1 comes first, and we could say 1 is less than 2, right? Because the point is facing the thing that's less than, okay, which is the 1. So 1 is less than 2. Is how you would say that. Okay? Now this symbol right here, let me get a different color. This means greater than or equal to. Either one could be true. And we're going to do some examples of that on the next slide. And then finally this guy means less than or equal to. Okay, so these are the 4 inequality symbols that we're going to be talking about. Okay, so I just want to get you guys comfortable with these and how they work and which way the point faces and things like that. So it's important to know that in math you can read from left to right or from right to left. So, for example, this guy can be said 2 different ways, okay? Since it is opening up, so the mouth is opening up towards the bigger number, but the point is facing the smaller number. If we read it from left to right, like we normally read things, we say 3 is greater than 2 because the thing is opening up towards 3. So 3 is greater, okay? If you read it from right to left, you start with 2 and you read 2, okay, the point means less than. So you would read 2 less than, because of that point, 3. Okay, so you can read it from left to right, 3 is greater than 2, or from right to left, 2 is less than 3. See how we do that? Okay, let's try the next one. So here is the greater than or less than or equal to sign. So that means that the 2 numbers that we're comparing actually could be equal to each other, or one could be less than the other. Either or would work, would make it a true statement. So the way that you can read this from left to right, you can start with 5. You can say 5 is, okay, point. That means less than. So 5 is less than, and since it has a line underneath, it's going to be less than or equal to. So 5 is less than or equal to 5, right? We read left to right. You can also flip it the other way and start with this 5 and read the other way. So if we start the other way, we can read 5. I see an open. It's opening towards 5, so this is greater than or equal to. Let me write this a little bit better. Okay, 5. So 5 is greater than or equal to 5. If we read it from right to left. Both of these things mean the same thing, and both of these statements are true. Isn't it true that the number 5 is less than or equal to 5? It's not less than, but it is equal to 5, so that is a true statement. One of those things is true. And isn't the statement 5 is greater than or possibly equal to 5? Isn't that true? Yeah, because it's equal to 5. It's not greater than, but or means one of those things need to be true for the statement to be true. Okay. So again, this is the greater than or less than stuff. You run into a point, it's less than, so 4 less than 2. No, that's not true. 4 is not less than 2. 4 is less than 8. 10 is less than 100. But you can also read it the other way. You can say 8 is greater than 4. You can say 100 is greater than 10. So that's how we deal with inequalities. So let's practice reading these in 2 different ways. So the first way is from left to right, and the second way is from right to left. Both statements are going to mean the same thing. So if we read this from left to right, we start at the leftmost number, which is 8. So we say 8 is, and then we run into a point. So that says less than. So 8 is less than, and then the next number, -1. So that's the first way to read it. That's from left to right. Now if we go from right to left, we start at the rightmost number, which is -1, and we say -1 is, we run into an open mouth, greater than, and then the last number. So that's from reading from right to left. So these 2 things mean the same thing. -1 is, well, actually this is an untrue inequality. How about we add that -8 to make it true? Let's make it a -8 instead. Okay, so that was, I guess inequalities can be untrue just like equations can be, but let's make it true just for the sake of practice. So if we read it from left to right, again, it's 8 is less than -1. That's true. From right to left, -1 is greater than -8. That's also a true statement. Okay, let's do the next one. So from left to right, start at our leftmost number, that's 7. So 7 is, we run into an open mouth, so that's greater than, or, because of the line underneath, equal to. So 7 is greater than or equal to 3. Now it's not equal to 3, but that's where the or comes in. Either one of those statements can be true. Either 7 is greater than, or it could be equal to. One of those, but in this case it's greater than, right? Okay, so that's from left to right. From right to left, we start at 3. So right to left, we say 3 is. Now, if we read from right to left, we run into a point, right? Reading from right to left. So that is less than or equal to 7. So either of these things mean the same thing. So reading it from left to right, 7 is bigger than or equal to 3. Reading it from right to left, 3 is less than or equal to 7. Okay, 2 different ways to say the same thing. Okay, how about this one? From left to right. So we have 6. So 6 is run into a point, less than or equal to, because of the line under, 6. Okay, from right to left, we start at this 6. 6 is run into an open mouth, greater than or equal to 6. Okay, so that's reading it from right to left. Both of these things mean the same thing. 6 is less than or equal to 6, and 6 is greater than or equal to 6. And in these cases, they're both going to be equal to, because 6 is equal to 6. Okay, what does this mean? What does this mean? X is greater than 3. So what this means, right, because it's not a number anymore, it's a variable. What this means is that X is a set of numbers bigger than 3. That's what that literally means. X is greater than 3 is an unknown set of numbers that are bigger than 3. Now, what numbers can you think of that are bigger than 3 that would be in this set? How about 4, 5, 6, a million? How about 3.000000001? Isn't that number bigger than 3? Yeah. How about pi? Pi is approximately 3.14. That's bigger than 3. So the point is that there's an infinite number of numbers that are bigger than 3, right? So how can we represent that with a picture? How can we represent all numbers, every single number bigger than 3 with a little finite picture? Well, we can just draw a number line, and we can say, okay, well, here's 0 in the middle, here's 1, here's 2, here's 3, here's 4, some other numbers. This goes on forever. And then in the negative direction, we have -1, -2, -3, and that goes on forever. And so to say that I want to show pictorially what it means to be a set where all numbers in the set are larger than 3, that means I'm going to start at 3 and I'm going to include everything that's bigger than 3. And I'll include it by shading, okay? So this is what that means. This is it. This is 3. X is bigger than 3. We put an open dot on the 3 to indicate that we're not actually including 3 in our set because 3 is not greater than 3. But everything else to the right of 3 is bigger than 3. So this is how we can graph these things on a number line. And there's, again, this is a finite picture. This is just a scribble of purple that I've drawn here, but what I'm showing you is that there are infinitely many numbers that are shaded here. We can't write them all out. Of course we can't write them all out, but the picture is saying that there is an infinite number because we're basically shading over this arrow that goes out to positive infinity. Okay. Alright, so this is some notation. We use closed dots when we have greater than or equal to or less than or equal to. We use open dots when we have greater than or less than. So like in this example, I used an open dot because we had a greater than. Closed dot means that we're including the point. Open dot means that we're not. So like we didn't want to include 3 because 3 is not bigger than 3. It doesn't belong to this set. Alright, so let's practice graphing some of these things on number lines. So X, first of all, let's read it from left to right. That's usually the way that we do it, but you can read it either way. So from left to right, we can read X is greater than 2. As we start at X, we have an open mouth, 2. So if I draw my number line, I don't have to draw these things perfectly, but I'm going to say that 2 is about right here. And I want to do an open dot on 2 because I have a greater than sign, which means strictly greater than. That means not equal to. So I don't want to include 2 in my set. And I want everything to the right of 2 because that indicates numbers that are bigger than 2, all the way to infinity. So like 3 would be included in that set. 4 would be included in that set. 1,000,000 would be included in that set. Right? So that's that. And you can test values too, right? You can say, well, is it true, just like with equations, is it true that 500 is in the set X? Is that true? Well, you go to your original inequality and you say, okay, if I plug in 500 in for X, is it true that 500 is bigger than 2? And that's yes. So yes, 500 is in the set. So that's how you can check yourself. Okay, now we want to graph X is greater than or equal to 2. There's just one small subtlety here. All right, that's different from the previous example. And that is the line under here. That means that we're going to include 2 in our point in our set, because what this set says, it says X is greater than or equal to 2. X is greater than or equal to 2. So that means that we can include 2 in this set. It's not like the previous one where it had to be strictly greater than 2. So I find 2 on the number line. I just make up a point where it should be, because a number line is infinite in length. I mean, the idea of it is, not the actual drawing, but anyway, at 2, we're going to go ahead and put a closed dot there to indicate that we're including 2 in our point, and we shade to the right. So everything bigger than 2 or equal to 2 is in this set. Okay, so is 2 in the set? Well, yeah, because 2 satisfies X is bigger than or equal to 2. When we plug 2 in here, is it true that 2 is greater than or equal to 2? Yes, it is equal to. So 2 would be in our set. Okay, let's do some more practice here. So how do we say this one? Reading from left to right. X is, okay, you always want to start with X is, and then I run into a point, so less than or equal to, because of the line underneath, -2. That's what that means. And I can show that on a number line by plotting -2 and showing the set that includes -2, so closed dot because of the line underneath, and everything less than -2. So am I going to shade to the right or to the left? Well, to the left of -2 is -3, -4, etc., etc. To the right of -2 is -1, 0, 1, etc., etc. Less than means to the left, okay? So everything smaller than -2 is going to be shaded. It's everything to the left. So that's my set. Alright, graph B is greater than 0. So I'm going to put 0 on my number line. I'm going to put an open dot on 0 to indicate that there's no line under there, and we're not including 0 in the set. And then bigger than means shade everything to the right. So anything that's larger than 0 is a valid point in the set. How about Z is greater than 1/2? Well, here's 1/2. And closed dot because of the line underneath the greater than symbol. And so how can I say this in words? I can say, and maybe I should have said it for the other one too, but this one is going to be Z, if we read from left to right, is greater than or, because of this line, so I run into an open mouth, so that's greater than, the line underneath says or, greater than or equal to 1/2. Okay, So anything that's larger than 1/2 or is 1/2 is in the set. So 1/2 is in the set, 2 is in the set, 93.6751 is in the set, things like that. So all of this stuff is in the set. So I'm going to shade to the right, all the way to positive infinity. Okay. All right, let's go the other direction. Let's write an inequality for the graph shown, and we're going to use x as our variable. So we're starting at 4, so this set is everything shaded in blue, and it says, okay, I'm going to start at 4, but I'm not going to include 4 because of the open dot. So everything to the right of 4 is going to be what? It's going to be x is greater than 4, and that is my answer there, right? Everything to the right of 4 is shaded. I'm not including 4 because of the open dot, so I left that without a line. Let's do another example. All right, let's use x again. So this time I am including -3 in the set, as well as everything to the left of -3. So everything less than -3, but it also could equal -3 because of the closed dot. So I could say that x could be less than or equal to -3. And that is my answer there. That is how I can express what this set is. Okay, so let's talk about solving inequalities. We can do this just like we did with equations. We take the same kind of steps. There's one little nuance that I'm going to show you, but essentially you work these out the same way that you work solving equations out. So if you have 2x minus 1 is less than or equal to 9, and you want to find your set x, you're trying to isolate x just like with equations. And again, you can think of this like an equal sign just for the purpose of solving. And you can draw a line through it, and you can move things around to get x alone. So I'm going to go ahead and do that. I'm going to look on the left side and say, well, if I want to get x alone, I can first undo subtraction by 1 by adding 1 to both sides. And doing that is going to give me 2x less than or equal to 9 plus 1 is 10. And finally, on the left, what I can do to get x by itself is I can divide both sides by 2. And once I do that, I get x by itself, which is what I wanted, is less than or equal to 5. So it's just like solving an equation, except instead of an equal sign, we have an inequality. And we want to graph this set on the number line, right? Now before, our set was just a single number, right? We solved equations, and we got a single number as our answer. This is an infinite number, okay? X is less than or equal to 5 means everything less than or equal to 5 is included in our answer. So, right? It's very different from x equals 5. That's one number. X less than or equal to 5, infinite, right? Okay, so how do we graph this on the number line? Well, we can start at 5. And then I want to indicate that everything less than 5 is going to be included in our set, including 5 because of that line underneath. So I'm going to put a closed dot at 5, and then I'm going to shade everything to the left. And that is my graph on the number line. Infinitely many numbers live there, right? And what's even really trippy to think about, if you guys, if you're interested in thinking about infinity, is that if you zoom into this number line, between 0 and 1, there are infinitely many numbers between 0 and 1, right? Think about 0.000000001. Think about 0.0213. Think about 0.1569846 repeating. I don't know. There's infinitely many numbers in this tiny little interval. It's pretty mind-blowing. And we'll get to more of that later on if you continue with math, but just a cool thing to think about is that there's as many numbers between 0 and 1 as there are between 5 and negative infinity. Okay? It's pretty cool to think about. Anyway, so got a little off topic there, but let's go ahead and move on and practice solving these inequalities. So we want to solve for the variable u. So again, I'm going to draw that line through there just like as if it were an equal sign, and I'm going to employ the same methods here that I used when solving equations. So I want to get u alone. I want to get my variable alone. So I work on the right side to undo subtraction by 11 first. And to undo subtraction by 11, I better add 11 to both sides. When I do that, I get u alone, which is exactly what I wanted. And I get u is greater than or equal to, reading from right to left, u is greater than or equal to negative 1. That is my set. That is an infinite set. That means in my set u, I'm going to include everything that's bigger than negative 1. Every single number bigger than negative 1 or equal to negative 1. Right? So in my set, I start at my letter, which is u, and I start at negative 1, and it says that, if I read it from, I always want to start with my variable, so I want to read wherever my variable is, and since my variable starts all the way to the right, I want to read from right to left to make sure that I start the sentence off with my variable. So how I would say this, I would say u is greater than, because I'm reading from right to left, I start with u and it's running into an open mouth. You see that? So u is greater than, or, because of the line underneath, or equal to negative 1. So starting at negative 1, I want to shade everything to the right of negative 1. My set u is greater than or equal to negative 1, so everything to the right gets shaded there. And that is my graph. This is my solution. Alright, which of the following values of v are solutions to this inequality? So it's just like equations where we can test values to see if it makes an equation true. Same thing with inequalities. We just test these values, we plug them into the variable, see if they make the inequality true. So the first one is negative 2, so we would just plug in negative 2 where we see our v, and we would get 1 bigger than 4, and then we're going to plug in negative 2 plus 9. And I can simplify the right side. This is negative 8 plus 9, which is 1. So this at the end of the day means 1 is greater than 1 when we simplify this. Is that true? Is 1 a bigger number than the number 1? No. It's equal to, but it's not bigger than. So this is not a solution. This is not true. What about here? If I plug in 4 in for v, and 1 is greater than 4 times v plus 9. Now simplify. 4 times 4 plus 9 is 16 and 9. Makes 25. So this says 1. Is 1 greater than 25? Is that true? Nope. 1 is not greater than 25, so this is not a solution either. Okay, what about negative 8? If I plug in negative 8 into v, into my original inequality up here, I have 1 is bigger than 4 times negative 8 plus 9. Simplify this to negative 32 plus 9 is what? Negative 32 plus 10 is negative 22 plus 9 is negative 21. So is it true that 1 is bigger than negative 21? Is that a true statement? Yes, that is true. 1 is a larger number than any negative number, in particular, negative 21. So yes, negative 8 is a solution that makes that inequality true. What about our final one, 6? So is it true that 1 is bigger than 4 times 6 plus 9? That's going to be no, because we have 1 is greater than 24 plus 9. So that's not a true statement. 1 is definitely not bigger than 33. Or looking at it the other way, from right to left, 33 is not smaller than 1. So the only solution was v equals negative 8. All right, let's go ahead and solve this inequality for x. So we're going to draw a line, solve for x. What do I have to do first to the right side to isolate x? Well, I want to undo the operation furthest away from x, which is subtraction by 2. So I want to undo subtraction by 2 by adding 2 to both sides. And when I do that, I get negative 6 less than equal to x over 5. Now I want to undo division by 5 by multiplying both sides by 5, just like I would with an equation. So those clear. And on the right, I'm just left with x. On the left, I'm left with negative 30. So this is my answer. And typically you write your variable first. So you could write it like x is bigger than or equal to, right? Because the mouth is facing towards the x. You want to keep that consistent when you rewrite it. So x is greater than or equal to negative 30 is our solution. Again, that's an infinite number of possibilities. All numbers bigger than or equal to negative 30. So here's negative 30. We're going to put a closed dot because of that line under there. And everything to the right is getting shaded because everything that's bigger than negative 30 is to the right. So that's my graph that goes with this solution. All right, let's try this one. This time our variable's y. Looking at the side with y, I want to isolate it. So the first thing I can do to get y alone is I can add 4 to both sides. When I do that, on the left I get 12, and on the right I get 4y. Okay. Now what I can do from here is I can divide both sides by 4 to get y by itself, which is what I wanted, just like when I solve equations. And 12 divided by 4 is going to give me 3. So this is 3 is bigger than or equal to y. Now I can, again, you can read from left to right. You can read from right to left. And typically when we write our answer, we put the variable first. We want to make sure that the open mouth is facing the variable, right? So that, you know, these two things match up when we flip the order. So this is read, y is greater than or equal to 3. Now if I plot this on my number line, this is anything that's 3 or larger. So 100 million is in this set, 1 billion is in this set, 1 trillion is in this set. So let's go ahead and put our closed dot there because of that line, and we're going to shade everything to the right. So that is my graph there. Okay, let's go ahead and solve this inequality for Q. So I'm going to draw my line through the inequality sign, and I'm going to work on the side with the variable, which is Q. And the first thing I'm going to get rid of is this subtraction by 12 by adding 12 to both sides. So when I do that, I get 8 on the left side, and then on the right side, I get 12 over 11 times Q. Now, there's a couple different ways you can deal with this. You can first multiply everything by 11 and then divide by 12. But remember, you can do this in one swift motion by multiplying both sides by the reciprocal. So what's the reciprocal of 12 over 11? 11 over 12. So that's what I'm going to do. I'm going to multiply both sides by 11 over 12. And so I get that Q on the right is by itself, which is what I wanted. Now on the left, when I do this multiplication, remember any number is understood to be over 1. Looking at the diagonals, I can cross divide before I multiply to save me some time. So 8 and 12 both have a divisor of 4, so 4 goes into 8 twice, and 4 goes into 12 3 times. Multiplying straight across, we get 22 over 3. Now, if you want to plot this, 22 divided by 3 in your calculator is approximately 7.33 repeating. So, we can write this with the variable first, as q is bigger than 22 over 3, right? Because, if we had x equals 22 over 3, or 22 over 3 equals x, rather, we could switch the order around to say this is x is equal to 22 over 3, and that's how we typically write it, with the variable first, so that's why I wrote it like this. But these two things mean the exact same thing. It's just a convention to write the variable first. Anyway, let's go ahead and plot this on a number line. So 22 over 3 could be right here, and q is going to be strictly greater than, which means it gets an open circle, and everything bigger than is going to be everything shaded to the right of 22 over 3. So that's my beautiful picture there. Okay, so here is the little nuance that I was talking about. Anytime you multiply or divide by a negative number, you have to switch the direction of the inequality sign. A lot of students forget this and mess up with it. But it's important, because if you don't do it, your inequality is going to be untrue. Okay? However, what we've been doing so far, adding and subtracting things to both sides, we don't have to switch the inequality sign for that. Only if we're multiplying or dividing by a negative number, okay? So for example, if we have negative 3 times x is less than or equal to 12, if I draw my line through the equal sign, what I have to do is divide both sides by negative 3, and when I divide by a negative, I need to switch the sign. Okay, so I need to flip the direction. So instead of the point facing this way, I need to face it the other way so that it's like this. Okay, now these go away, and I get x is greater than or equal to negative 4. Okay, so what would have happened if I didn't flip that inequality sign? Well, my original inequality was negative 3x is less than or equal to 12. So what would have happened if I just divided both sides by negative 3 without switching? I would have gotten x is less than or equal to negative 4, right? Without flipping it, which is the wrong thing to do. And why is it the wrong thing to do? Because what this says is that anything that is smaller than or equal to negative 4 should satisfy this original equation. Consider x equals negative 5. That's in this set, right? It's smaller than or equal to negative 4. So if we plug in negative 5 into the original equation, we get negative 3 times negative 5 less than or equal to 12. We get 15 is less than or equal to 12, which is not true. That is not a true statement. So that's what causes the issue there. But here, when we flipped it, now this is true, right? Because my original equation was negative 3x less than or equal to 12. So this says that anything that's bigger than or equal to negative 4 will satisfy this. So if you plug in, for instance, something like 0, 0 is bigger than or equal to negative 4. If we plug in 0 here, we get negative 3 times 0 is less than or equal to 12. Negative 3 times 0 is 0. 0 is indeed less than or equal to 12. So that is a true statement. So just remember, whenever you multiply or divide by a negative number, you need to flip the sign. Alright, so let's take a look at some examples where we do have to flip the sign. Now, this first example, u divided by 3 is greater than negative 9. Alright, we need to undo division by 3. So what I'm going to do is I'm going to multiply both sides by 3. And that clears, and I'm left with u is bigger than negative 27. Now notice, I did not flip the sign. I did not need to flip the sign because I just multiplied both sides by a positive 3. I didn't multiply both sides by negative anything, right? The only time you flip it is if you are physically multiplying or dividing by a negative, okay? And you can always check yourself by testing your solution set into the original inequality, okay? So like testing numbers from it, just like we did in the previous slide. All right, so this is our solution, and you can plot it on a number line. You don't have to, but you can. Let's go to the next one. We have negative 2x is less than or equal to 8. Now, how do I get rid of the negative 2 being multiplied by the x on the left? I need to divide both sides by negative 2. And at this point, you should say, whoa, I'm dividing by a negative. I need to flip the sign. So let's go ahead and flip this the other way so that the point is going in the opposite direction. Now, negative 2 divided by negative 2 is a positive 1, giving me x by itself, which is what I wanted. 8 divided by negative 2 is a negative 4. And so that is my answer right here. X is greater than or equal to negative 4. Let's take a look at this example here. We got negative 3x plus 1 is less than 7. First thing I'm going to do to get x alone is I'm going to subtract 1 from both sides. And when I do that, I get negative 3 times x is less than 6. Now what I need to do on the left is I need to divide both sides by negative 3. Oh, I'm dividing by a negative. I need to flip the sign, y'all. When I divide both sides, the sign's flipping. Okay, so I'm going to make the point go in the other direction. And I get x is bigger than negative 2. And that is my answer here. Okay. All right, next one we have 2x plus 1 is greater than 3. Let's go ahead and subtract 1 from both sides. I don't need to flip anything because I'm adding or subtracting. I'm not multiplying or dividing yet. I get 2x is bigger than or equal to 2. Now I need to divide both sides by 2. And I'm not dividing by a negative, so I don't need to flip anything. It just stays in the same direction throughout. And my solution is x is bigger than or equal to 1. Alright, let's do something like this. Alright, just like an equation, we want to group our variables on one side and then start solving. So the first thing I'm going to do is I'm going to undo subtraction by 3v by adding 3v. Notice that I'm not multiplying or dividing by a negative, so nothing's getting flipped quite yet. So on the left, I'm left with negative 32. On the right, 4v and 3v make 7v plus 24. Now, on the right, I need to subtract 24 from both sides, giving me negative 56 on that side, less than or equal to 7v. And on the right side, I need to get rid of the 7, the multiplication by 7, by dividing both sides by 7. Now notice I never divided by a negative number. I never multiplied by a negative number, so that sign is going to stay in the same direction through every step. So I get v is greater than or equal to negative 8. And if you like to write your variable first, which you should get in the habit of doing so, we'll write v, open mouth, under the line, negative 8. Line under. Let's try this one. Alright, so I need to use the distributive property first of all. So 4 times 3w is 12w. 4 times positive 9 is positive 36. So I just wanted to get rid of that to start out with. And now I want to group my w's together. So I'm going to start by subtracting 7w from both sides to get the w's on one side. And I get 5w plus 36 is greater than or equal to 6. Let's go ahead and subtract 36 from both sides. So I get 5w greater than or equal to negative 30. Finally, divide both sides by 5. To give me W is greater than or equal to negative 6. Notice throughout each step, I never divided or multiplied by a negative number. I did subtract a few times, but remember with subtraction, you don't have to flip anything. So since I never multiply or divided by a negative, the sign stays in the same direction. Padma sells tickets to customers for $8 a ticket. Padma already has $22 in sales so far. How many tickets does Padma need to sell so that she makes at most $300? So let's unpack this word problem, what it means in terms of inequalities. Now, what's our unknown value here? What are we trying to figure out? Well, we're trying to find out how many tickets she needs to sell. So I'm going to say that T is going to be our unknown, that's our variable, and that's going to be the tickets that she needs to sell. Now, she's already made $8, or sorry, no. She's already made $22 in sales. So we're going to take 22 and we're going to add on $8 a ticket. So $8 for every ticket. So that's our expression there. And we want to know how many tickets does she need to sell so that she makes at most. What does at most mean in terms of inequality? So at the most 300, could it be 299? Yes. Could it be 298? Yes. Could it be 300? Yes. So we want this expression right here to be less than or equal to 300. Okay? And so we set it up. Now we just have to solve it. So let's go ahead and subtract 22 from both sides. And we get 8t is less than or equal to 278. Alright, and now what we need to do to get t by itself is we need to divide both sides by 8. And we get that t is less than or equal to 34.75. Okay, so now we're talking about tickets here. So at the most, she wants to make $300. So we need to round down, basically, right? Because if we were to put 35 into this equation, let's say we round it up and we put 35 into 22 plus 8t is less than or equal to 300. And we put 35 in there. So we got 22 plus 8 times 35. Is it true that that's less than or equal to 300? Let's see. No, we get 302 is less than or equal to 300. So that's not true. That's why we have to round down to 34. So t is, because we can't have a fraction of a ticket, right? That doesn't make sense. So our answer here is going to be t is less than or equal to 34.